So we'll just start the sharing session. Hello, everyone. Welcome to Dapp Learning sharing session. Dapp Learning maintains open source Dapp development tutorials on GitHub. As a developer community, we hope we could not only give junior developers an executable and simple Dapp Learning roadmap, but also present advanced developers with a platform for communication and cooperation. So today, we are very pleased to invite Nathan Holland, the lead protocol engineer in O1 Labs. Nathan, could you introduce yourself first?
Sure, yeah, I'm Nathan. I'm a protocol engineer at O1 Labs, where we work on Mina protocol.
It's really our pleasure to have you here, Nathan. Next, Nathan will introduce zero knowledge proofs in Mina. Nathan, I'll leave it to you.
Okay, let me present my screen real quick. Okay, so as I said, I'm Nathan, and today I'm going to talk about zero knowledge proofs in Mina. So first off, what is Mina? Mina is a new layer 1 blockchain protocol that we've built from the ground up to be the world's lightest blockchain. What does that mean? It means that anyone can run a full node. You only need 22 kilobytes of data to join the chain as a full node. It also has a light and decentralized consensus mechanism, so there's no cap on the number of validators, and there's no need to keep the history of the blockchain on disk, so it's lightweight for consensus nodes to join and operate. Mina is scalable and trustless, so what that means is that you can verify the entire chain quickly with minimal hardware and not much data. It only takes a few milliseconds to actually verify the entire blockchain. Because of that, there's no need to trust third parties for additional data, even when you're on the web or mobile devices, which makes it more secure and more trustless. And additionally, Mina includes a novel ZK Snark-powered smart contract system, which we call ZK apps. They can privately use off-chain data, and there's no need to store any information on the network. And replay contract executions forever into the future, like blockchains like Ethereum work. And so how does that actually work? So when you get a Mina block and you look at the blockchain, instead of verifying the entire chain from the beginning, every single Mina block has a proof with it that attests to the correctness of the entire blockchain. So participants just have to verify a single recursive zero-knowledge proof in order to know that the blockchain is valid instead of having to look back at all the previous blocks. Full nodes in the blockchain only store this proof. They don't need to store the entire chain. And because of this, Mina can be accessed from any device instantly forever. By comparison, Bitcoin is about 300 gigabytes in size. And from scratch, if you had all that information available locally already, it takes about 6 hours to access this from a $2,000 desktop machine. Ethereum, by comparison, is 750 gigabytes. And it takes even longer to sync to because you have to play back all the smart contracts as you do so. So now that we've talked a little bit about what Mina is, let's talk a little bit about how ZK Snarks work before we dive into how we use them in Mina, just so that we have a good understanding. So a snark is a succinct, non-interactive argument of knowledge. So basically what it is you are making an argument to somebody else about knowledge that you have. And the ZK part is just saying, zero knowledge, that we can hide some of that information from the other party. So we're making an argument about knowledge, but some of the knowledge we're making an argument about, we can keep private from the other person. So if you want to have a series of parties interact with each other using ZK Snarks, the first thing you would do is you would set up a set of constraints ahead of time. So all the parties would agree, like, here is a set of constraints that, if they're all satisfied, would prove something to us. And then if somebody, in this protocol wanted to then generate a proof, they would take some inputs into the constraint system that are divided into public and private sections and evaluate them on the constraint system, and then generate this small little proof at the end. And this proof is only going to be, in order of like hundreds of bytes in size. So it's a pretty small little proof. And then if you want to verify that information, what you can do is give the proof and the public inputs to another party, and they can take those both and then verify like either the proof is valid or the proof is invalid. And that tells the verifying party a couple things. It tells the verifying party that the prover had a set of inputs that satisfy the constraint system, and it also tells the verifier that the public set of inputs they provided were the same public set of inputs they put into the constraint system when they generated the proof. So this allows you to sort of like attest to information in the private data, like make a commitment to private information, and then prove some kind of commitment to that private information to another party. So just picking on a really silly example of like a statement that you could prove in a snark. Here's a really arbitrary one. This is a snark circuit that describes a constraint system that says, I know two numbers that when you add them together, they sum to 10, which is really a very uninteresting proof. But this sort of lays the framework for how you can visually think about how these snark proofs can be constructed. As long as we can lay out snark proofs or the logic we want to put in the snark proof as like a left to right flowing diagram like this, then you can build a snark for it. So on the left side here, we have like two inputs, 3 and 7. Each of those could be like either public or private. So we could keep both the numbers private. We could keep just 7 private, and then give 3 to somebody and say, hey, I know a number that when you add it to 3 will equal 10. But what you'll notice here is that because we have to put everything into sort of this left to right diagram, a single snark proof, the statements that it can make, or the statements that it can prove within a single proof, have to be definitive. So I could build a circuit that proves that I know 5 sets of numbers that add to 10, but I couldn't generate a circuit that proves a dynamic number of pairs of numbers that I know that sum to 10. So for example, I have to always like statically choose a number of statements I want to put into my proof ahead of time. So there's no way to dynamically like say, oh, I know 7 or I know 9 different statements that meet the same constraint system within one proof. Except that there sort of is. There is a way that you can do this, which is to use recursion in the proofs. So in addition to making constraints about numbers and arithmetic in the snark circuit, you can also make a constraint in the snark circuit that says that we know about some other snark proof that is also valid. So if we extend this example to say that I know 2 numbers that sum to 10, and I know some previous proof of the same set of statements that is also valid, now what we can do is we can chain proofs back to back. So every single proof proves a single statement here about numbers we know that sum to 10, but we can keep on chaining proofs into each other such that any proof in proves not only that we knew 2 numbers that sum to 10, but all the previous proofs preceding proof n are also valid. So we know any number of any set of pairs of numbers that sum to 10. And so this is usually referred to as recursive composition in the world of ZK snarks, because we are recursively composing the prior evaluation of the constraints within the constraints themselves. And this allows for any number of proofs to be verifiable from within a single succinct proof without growing the size of the proof. So even after you add 1,000 of these proofs into each other and you compose them into each other, the final proof that you have at the end is still that same succinct, few hundred bytes value. Because these proofs are zero knowledge, we do not need to maintain prior proofs since they can be included as private inputs to the constraints. So we're left with that final proof at the end, and there's no reason to even keep the previous proofs that we've generated around because we've already encapsulated the statements that they make into our newest proof, and they were private inputs to that proof, so we don't need those previous proofs to actually verify the most recent proof that we have. And in my opinion, this is really the coolest thing about ZK snarks. This is what makes them so powerful. It's almost sort of like magic because you can prove an infinite number of statements in a succinct value while keeping verification O(1) in cost. And all at the same time, you don't have to reveal any of the inputs to the statements. So you have complete choice over which information you hide and which information you expose along the way. And this is a property of ZK snarks that is heavily exploited in Mina in order to achieve our vision for blockchain. So now that we understand a little bit more about ZK snarks, let's talk about how we actually use them in Mina to make our final succinct proof, the single proof that proves the entire blockchain. So there are two kinds of proofs in Mina. The first kind of proof is a transaction proof, and the second one is a blockchain proof. So let's start by taking a look at transaction proof. So for every transaction that happens in Mina, there's multiple statements we need to prove. We need to prove that when the transaction was applied to a previous ledger state, that it correctly achieved a new ledger state. So in Mina, ledgers are represented using Merkle trees. So what that means is we have this, succinct hash at the very top of the ledger that identifies all the contents of the ledger. So the way we codify this in Mina is to say that, if you apply the transaction to some Merkle root X, it will achieve some ledger of Merkle root Y. In addition to that, you'll also prove that the transaction was authorized by the sender, so that the transaction has a valid such that the person who's actually sending funds from one account to the other actually authorized it. We also prove things like any funds that were introduced to the ledger are in accordance with the inflation schedule and were awarded to the right parties. And additionally, we prove things like third-party proofs that are purchased from other members of the network within the ledger are properly paid out. So we'll talk a little bit more about what this means later as we continue going through the presentation. But these are some examples of some of the things we prove when we apply transactions. And so let's just kind of look at that in a little more detail. This is going to introduce a little bit of notation that we're going to see later. So one way of thinking about a blockchain is as a state transition machine. So if you think about it that way, each ledger that is achieved by the blockchain is a state, and each transaction that you apply to ledgers is a transition from one state to another. So in this example, we have our transaction, which sends 5 Mina from account A to account B. And if we apply this transition to the ledger state SI minus 1, then we're going to get ledger state SI. Because each of the ledgers here is a Merkle ledger, we don't actually need to input the entire ledger into the snark circuit. So we don't need to take the state of every single account in the entire system and then load that into the circuit in order to generate the proof. Instead, what we do is we can actually generate Merkle proofs that there are some accounts in these ledgers at each position. And then just input those Merkle proofs. So we now know that there's some member in the set of this ledger at this location associated with this account, and it had this balance. And then we can do the same thing for the target ledger we're achieving. It's actually a little mistake on this slide. The account states are not properly updated in the ledger on the right, but hopefully the point is understood here. So at a high level, that's how the transaction proof works. And we generate this proof for every single transaction in the system. And then we have a blockchain proof, which we generate for every single block in the system. So the blockchain proof makes a few statements. It says that the previous block has a valid proof. So that's our first level of recursion. It also says that all transactions in the block have valid proofs as well. Now, this happens with delay, and we're going to go over this some more later. It'll make sense why, but for now, just think about it like the blockchain proof is saying immediately that all the transactions in this block are valid. We'll get to the details of why it's not quite like that later. But ultimately, all the transaction proofs are eventually merged into all of the block proofs, so that you have this one block proof that's proving all the previous block transitions and proving all the transactions that were ever in the blocks as well. And the blockchain proof also states that the block was produced correctly according to the consensus rules. For example, we're a proof of stake system. So one of the statements that it would prove is that the person producing this block had enough stake to actually, be allowed to produce this block at this point in time in the network. So diving into that with a little bit more detail, this diagram shows how blockchain proofs are composed. So this diagram is also missing some arrows, unfortunately, but if you look at a proof Pn plus 1, that is associated with block Bn plus 1. And for that proof, there will actually be 3 inputs to here. We're going to first look at the previous proof, proof Pn, and we're going to say that this was a valid snark proof. And then we're going to look at the previous block, block Bn, and we're going to say that this is a block that was associated with this proof. So basically, we've proven, we verified the snark proof Pn, and then we verified that Bn is the block associated with that snark proof. And then the third input that's missing from this diagram is that block Bn plus 1 is also an input to proof Pn plus 1. And in that case, what we're looking at is we're looking at the transition from block Bn to Bn plus 1. This is where we actually check the consensus rules. So we say that we know that block Bn is valid, and Bn plus 1 is an extension of the previous block that is valid according to all the consensus rules. And this is how we recursively compose all the blockchain proofs into each other, and then we're just left with one proof for each block that actually proves both that block is valid and every previous block is valid. So looking at that model as a whole from a higher level, the way you can think about this system is that every single block contains in it a batch of state transitions. And so they're like, these big step transitions between states. You apply all the transitions back to back. It takes you from one state to another. And so if you really look at this diagram and you think about all the information that we need to prove, there's a lot of proofs that we have to generate for each of these block transitions. The first thing we need to prove is we need to prove that the transition between the blocks themselves is valid, as we discussed earlier. You need to also prove that each transaction is valid on the previous ledger, and then prove that all these transactions take you to the correct ledger state ultimately at the end. So doing this for every single transition, for every single block, and then making the statement for every single block is really a lot of proofs to generate if you do it naively. And this would have a really bad effect on block proving time, because if I'm a block producer and now I have to generate all these proofs for every single transaction I want to include in the block, it's going to have a negative effect on block time and a negative effect on TPS as well. So it's not really scalable to just require all of these proofs to be generated within the amount of time that's allocated for producing blocks. So, one way of solving this problem is to build sort of like a queue where each block will actually, instead of immediately trying to generate proofs for each transaction and then including them at the time of block production, it will instead put the transactions onto a queue of transactions that it wants to have proven by the network. And then the network can asynchronously, in parallel, go over all of these transactions, generate proofs for them, and then sell them back to the block producer. And this whole system of sort of farming out snark work to be done, proofs to be generated, and then selling them back to the block producers at a fee is known as the snark at place. It's a whole sort of layer 1 economy that we have on our blockchain that's unique to us. And what it allows you to do is it means that whenever you include transactions in a block, the block you just produced isn't immediately including proofs of those transactions, but the protocol requires that they have to be proven in order for the blockchain to move forward, and some future block producer will end up actually including proofs of your transactions in a future block that is produced on chain, which is what this diagram is showing here. So this makes sense, but in practice there's still a problem, which is that because this is a queue, we can't really parallelize over it. We have this queue of work that we want to do, and we have to go through this queue of work sequentially on the network and sort of do one proof at a time, because as we saw before, if we look at like how the blockchain proofs are composed, you need to have the proof for the previous block before you can generate the proof for the next block. So there is a further solution to this problem, which is to basically structure all of the transactions that you want proven on the network into a tree. So what you want to do is you want to take all of these transactions you have and you want to compose them into one final proof, instead of sequentially composing them one after another so that the proof for transaction 1 includes the proof for transaction 0. What you can do is you can put them in a tree, and have the network prove all the transactions individually in parallel. And the network can do these in parallel because the only thing you need for each individual transaction proof is to know what the ledger state was before and what the ledger state is after each transaction. So you can pre-play all the transactions back to back. You can generate the Merkle proof witnesses for each of these transactions. And then all you have to do is just on your machine, take each of the Merkle proof witnesses and input them to whatever transaction you want to do some work for. And so that allows the network to generate all these base proofs in parallel, but we still have a problem, which is that we have 4 proofs now that we want to merge into a single proof. So in order to do that, we can, in a binary tree fashion, sort of merge together 2 proofs at a time. And so now, these proofs, these base proofs for 0 and 1 are now merged into a single proof together that encapsulates the statements for both 0 and 1, and same for 2 and 3. And then we can take each of these merge proofs and merge them again. And so you'll notice, if you're familiar with a map reduce, you'll notice this operation is very similar to a map reduce when you look at this tree, because you're mapping over all the transactions at the bottom to generate base proofs, and then you're reducing all the base proofs into merge proofs, which can ultimately be included into the blockchain proof. So what that gives us ultimately is a picture that looks a little bit more like this. We have this data structure we call the parallel scan state, which is essentially a queue. It's a queue of trees. So every single tree in the queue has one less layer than the tree after it, because as you complete layers of the tree and you do work for it, you can sort of throw off the last layer. And so you have this fixed size queue of trees that block producers can put work into, but in order to make space for new work we put into the queue, they have to also finish work on the other side of the queue. So they have to purchase work from members of the network called snark workers who produce proofs, and then include them into the left side of the queue to free up space. And then they can now have space to actually put new transactions into the right side of the queue. And this is the system that enables us to quickly produce these blockchain proofs while still having the blockchain proofs encapsulate all the statements of every single transaction we apply on the network. So that's an overview of how zero-knowledge proofs are utilized in Mina to create our succinct, our final succinct proof in the blockchain. Let's talk a little bit about how smart contracts work in the system. So first, let's review how smart contracts are traditionally implemented. On a traditional network, like Ethereum, for example, when a user wants to execute a smart contract, what they'll do is they'll first send a transaction to the network to trigger the execution of the smart contract. This transaction will get broadcast around the network, included in the mempool of a whole bunch of nodes that are operating on the network. And then eventually, when one of those nodes produces a block, it will include the smart contract execution into its block. So the block producer will basically load up a VM, it will execute the smart contract, and then it will put that smart contract into the block and set the state that was achieved after executing the smart contract as the new ledger state that's achieved by applying the block. As every single node receives this block on the network, each of those other nodes has to also re-execute the same transaction. So they have to also boot up, they don't know if the block's valid yet, so they have to look at all the transactions in the block and verify them against the previous ledger state. And in order to do that, they have to, similarly to the block producer, boot up a VM, execute the smart contract in order to know that the block producer correctly executed the first time. So every single time somebody wants to execute a smart contract, it executes not on their machine, but on every single node on the network. Then when somebody wants to bootstrap to the network from scratch, if they want to bootstrap in a trustless way, where they don't have to trust any other parties, meaning they basically need to verify the blockchain from scratch, they would first download all the blocks in the blockchain, and then they would go through and they would execute every single smart contract that was ever submitted to the blockchain. So it's an O of N operation where we connect to the network, and then we do that same process of loading up a VM, executing the smart contract, and validate all the ledger states that we achieve. Now, in practice, this is really, really expensive, and so many node operators on some of these chains choose to actually trust other nodes of the network that they have already verified the state, rather than doing full verification. And if you ever use a web browser to interact with a DApp, then you have also done this yourself, because as a DApp, you are trusting whoever is providing the web API into that blockchain that they have verified the state of the blockchain. So you are, in a sense, also in that situation, putting trust in another party that they have not manipulated the blockchain, that they're not lying to you about any information. You really don't know without re-executing every smart contract that they're telling the truth. So if we look at how ZK apps work in Mina, they work a bit differently because ZK apps and Mina are powered by zero-knowledge proofs that we kind of merge together into this one final zero-knowledge proof, as we discussed before. So when I want to execute a smart contract on Mina, what I would do is I would generate that proof locally on my device. And this sends a transaction to the network containing that proof. Once that transaction is included in a block by the network, it eventually gets snarked in that system we talked about before, the parallel scan state. And so that means that the proof is merged up. We end up with one transaction proof at the end, and that transaction proof is merged into our blockchain proof. So when we look at the block on the network, when we receive that block and have to validate it, all we have to do is just check the blockchain proof. And that tells us that the ZK app that was executed locally by this user is valid, because the proof they generated gets merged up into that whole transaction proof system. And so also that means that when a new node bootstraps the network and they join the chain, all they have to do is just download the latest blocks and check the snark proof for the best of those latest blocks. And that allows them to bootstrap to the chain in really a very short amount of time, because they don't need very much data. And the operation of actually verifying all the execution of every smart contract forever is very cheap. So hopefully that all made sense. As one last topic, let's talk a little bit about how we can leverage Mina's ZK apps infrastructure to empower ZK DApps, zero-knowledge DApps on other chains as well. So there's a lot of interest today in zero-knowledge proof features on Ethereum and other blockchains, but there's a problem with zero-knowledge proofs on Ethereum, which is the high gas cost for evaluating them on the EVM. Every single smart contract you have that verifies zero-knowledge proof is very expensive. It costs a lot of gas to actually execute it. So what can Mina do to help solve this problem? Well, since Mina provides a system in which all the zero-knowledge proofs that are ever executed are rolled up into a single proof on the entire blockchain, we can utilize a bridge from Mina to Ethereum and share all of the cost of verifying the smart contracts across all the DApps on Ethereum with a single smart contract for Mina. And in fact, we are already coordinating with the Ethereum Foundation and the Mill Foundation to make this work happen. So how does it actually work? We create a smart contract in Ethereum that can verify Mina's blockchain proof and consensus choice. Anyone has permissions to update the smart contract with a new Mina state. So whenever new blocks are produced on the network, anybody can go and actually update this smart contract on Ethereum with those new blocks. And the smart contract is able to run Mina's consensus algorithm to look at those blocks and make a choice about which of those is better. I didn't really talk about this before, but Mina has a unique succinct consensus algorithm that allows us to just look at two blocks and look at the data to test it to in their proof and make a choice between those two blocks without any historical information. So we can encode that into the Ethereum virtual machine and allow anybody to send a block, and then the smart contract can reason about which block is better, the block that the contract already knew about or the new block that somebody's sending to the network. And now that you have the smart contract, multiple applications in Ethereum can access zero-knowledge proofs generated on Mina's ZK app system through the same bridge smart contract. Instead of having, n different smart contracts in Ethereum that all have to pay gas cost for verifying their proofs all the time, all they have to do is look at a single Mina proof generated by a single smart contract. And that will tell them not only that, whatever proof they're currently interested in is valid, but any prior proof that they had ever sent to Mina before and had evaluated on Mina's smart contract system is also valid. You basically reduce the number of verifications you have to have in the total Ethereum ecosystem and can share the gas cost, which is really, I think, a big help to trying to bring zero-knowledge proofs to DApps on Ethereum and other networks. So we'll touch real quick on some of the possibilities with ZK apps on Ethereum. So one example of something you could do is private Dow voting. So you can collect decentralized autonomous organization votes on the Mina chain for DAOs that exist on Ethereum, and then provide a proof that a certain vote met a threshold or that a party won an election, and provide that proof back to Ethereum. So what it allows you to do is hide the actual voters, as opposed to today where DAO votes have to all go publicly on the Ethereum blockchain, so everybody knows who voted for what. Another really good use case is bringing in real-world financial data. Because Mina's ZK apps are zero-knowledge proof powered, you can include private information to a ZK app execution that can attest to financial information in the real world. We have a project, I think it's called HTTPS Oracles, or it might be renamed now, but it basically leverages HTTPS, which includes private public key security, to ensure that you're talking to who you think you're talking to verify authenticity of information that you receive over a web request. So for instance, I could make a request to some bank that I work with, and then I could have a snark proof that attests that over the last 6 months of banking with them, my balance was above a certain minimum threshold. And then I can provide that proof back to Ethereum in order to get like an under collateralized loan on Ethereum, without having to ever reveal who I am or what my bank account is or exactly how much money I have. I just prove that it's above some threshold the contract let them know about. Because ZK apps can be used to prove properties of membership without revealing identity, it can be used for proving things like NFT ownership. It can also be used for, in general, proving ownership of assets that are on Ethereum. So really any data that's on Ethereum can be input to ZK apps and then anonymized through the use of ZK apps and provided back to Ethereum as a zero-knowledge proof. There's also the use case of zero-knowledge powered games, so such as asymmetric strategy games. I know one game out there is Dark Forest that runs on an Ethereum sidechain, I think. It has very high gas costs, but if you were to use something like Mina's ZK apps, you could actually run the game on Mina and then just have the proofs provided to Ethereum to run other aspects of the game that are more public. So Dark Forest, for those who don't know, is it's like a strategy game on Ethereum that uses zero-knowledge proofs to provide like a fog of war. So every person who's playing the game can only see like a certain portion of the map, and zero-knowledge proofs are used to hide information from different parties based on what they do. And then another use case is interacting with private enterprise data. You can import private enterprise data into Mina ZK apps and provide proofs of that information to Ethereum. And Mina also has plans to provide a rollup interface for the Ethereum blockchain natively within our ecosystem, which we call ZK rollups. So having this zero-knowledge bridge between Ethereum and Mina would also allow Ethereum to dispatch new ZK rollup tasks to Mina. So Ethereum smart contracts can say, oh, I want to do more. I want to execute, like, we produced 500 blocks since the last rollup. Now let's roll up the last 500 blocks and get a smart contract for that. And so as you do all of these smart contract executions, they would all be available within that single Mina proof that's imported to that one Ethereum smart contract. So that's all I wanted to talk about today. We do have a website. We have a Discord. If you're really interested in learning more about ZK apps, I highly recommend joining the Discord. You can look for the O1 Labs developers there. We'll be around to help support people as they want to learn about it. We do have our own smart contract programming language that's embedded in JavaScript that we developed called Snarky.js. It's ready for use. ZK Apps is not live yet, but there are still different things that you can build, and there's some documentation, and we're really interested in onboarding new developers to our system, which we're hoping to launch very soon. So with that, I have some time for Q&A if anybody has any questions.
We have collected some questions from our community members. I'll just ask these questions on behalf of them. Okay. So, what is the data for reconstruction reconstructing the Mercury tree stored? Does a new node rerun all transactions to build the world state, or they just reload some key value paths to rebuild the tree?
Sorry, is the question where is the ledger state stored for Mina in order for us to input data to the proofs?
Yeah.
Yeah, so there's a consensus node is a concept on our network as opposed to a non-consensus node. So if you want to produce blocks or you want to produce new work for the network, you need to have a copy of the ledger state locally. So the ledger is stored on a certain subset of nodes in the network. And then those nodes all have access to generate any of the proofs that full nodes are interested in, as well as the proofs that are required to input to our snark circuits.
Okay. The second question is, what's the performance of Mina on transaction confirmation per second?
Yeah. So when we've been building out Mina, we've been building out with decentralization and privacy and zero knowledge proofs in mind first. So our current TPS performance is not really great, but it's been on purpose that we haven't really been focusing on it because we know that we're able to scale that further in the future. We've just been focusing on trying to bring zero knowledge smart contracts to the blockchain. So the current TPS, I got to look up the numbers. I want to say it's 0.2. I think we'll be able to bump it up in the future, not too far away. But yeah, like I said, it's low because we haven't been focusing on it. It's sort of something we want to work on after we get the smart contract system out to make that.
Okay, sure. Next question, what's the depth of Mercury ledger?
The depth of the Merkle ledger, I want to say it's 20 right now. It's either 20 or 30. I'd have to, if you message me about it later, I can look that up for you.
Okay, I'll message you later. Next, how to decentralize the operator?
The operator being who? If you mean like the smart contract, like applications that connect to the Mina chain and execute smart contracts, they are already decentralized because they generate the smart contract locally and are able to sync to the blockchain without really any extra data. So,
okay. Next question: how Mina orders the transactions? How Mina orders those transactions?
The block producers choose how to order the transactions. For ZK apps transactions, there is sort of a way that you can bundle a whole bunch of party operations that are related to each other in a single transaction. So if you have a interaction with multiple parties that sort of needs to happen all at once, you can bundle them all together into a single transaction. And then otherwise, transactions in the network have to be submitted with a nonce. So you sort of, ahead of time when you submit them to the network, you enqueue them, and then block producers pull them off of their transaction pool and include them in whatever order they see fit, so long as they apply.
Okay, I see questions in the Google meeting. Dixon said, I see that recursive proof and ZK snark are also widely used on Ethereum ZK rollups. Why did Mina choose to do an L1? Is Mina a competitor of Ethereum, and what is the future market positioning?
I don't know if I would say we're a competitor with Ethereum. I think there's a world in which both of us operate next to each other, as I mentioned with the ZK bridge. But I think, what ZK rollups do is they roll up only the verification of the correctness of a chain. So it allows you to skip some of the extra steps of joining a chain. You get some of the benefits of Mina that way. But a ZK rollup requires you to sort of do this outside of your protocol. In an L1 like Mina, you can keep it succinct forever and immediately succinct. And by having zero knowledge proof capabilities already available to the smart contract system, it really makes all the different interactions you can have so much more powerful, because now you can have smart contracts that each have different zero knowledge proofs in them, interact with each other in a more seamless way, and then have that very quickly and immediately encapsulated into a single proof.
Okay. I see another question. What does the Web2 data provider need to do in order for Dapp to bring the Web2 data into the Mina chain?
So if you wanted to have a Dapp that used the Mina chain, what you would do is you would write a smart contract on Mina for the zero knowledge proof portion of your Dapp. So I'm assuming you're already a Dapp developer. You have a Dapp that lives in Ethereum. The assets for the Dapp are on Ethereum. Whatever zero knowledge proof you would want to generate that you would normally embed into Ethereum smart contract, you would write an application for that in Mina. And then what you can do is send transactions to Mina to make those execute, and then just have the smart contract, once the Mina proof is available for that on the updated Ethereum smart contract, just have the smart contract reference that latest Mina block is available to say like, hey, you know, I submitted a proof to be generated to Mina, it was generated, and here is the proof that shows that my proof was valid. And then the smart contract can continue execution.
Okay. Another question, what is the progress of ZK app development? When will it be launched?
Yeah, ZK apps development is basically done at this point. I think there's a couple of small details that are being put on top, but it is, we've really made a lot of progress. In terms of when it'll be out, soon. I can't really give an exact date, but we have an incentivized testnet that we're launching that should be really soon. So you can look forward to that. I recommend getting involved if you're interested in that. And then after we do some testing there, we'll be able to launch the mainnet.
Oh, okay. Okay, another question from the Tencent meeting. Safe interoperability of private enterprise data with public smart contracts sounds like a very promising application. Are there any related applications?
Any like ideas for applications or any related applications?
I think he asked about the private enterprise data with public smart contract.
I don't have a good example off the top of my head of applications that can be built with that. Yeah, sorry, I don't think I'm the right person to ask for that.
Okay. I think our last question. All developers in our community are quite interested in zero knowledge, and they are actively learning it by themselves. So do you have any suggestions or tips or learning roadmaps to share with us?
Yeah, I mean, zero knowledge proofs can be pretty hard to get into right now because it's a very new field. There's not really a set standard right now. So, you know, we're building our own programming system for programming ZK snarks. I think that what our team has built is really good. So I would recommend checking out Snarky.js. I think it serves as a pretty good introduction, but there's also a lot of other tools out there that are documented and available in good tutorials. So I think that, you know, just pick a smart contract language that looks like it has good documentation, start playing around with it. And whatever you learn there is transferable to other smart contract languages that you pick up. But I think programming them is probably the best way to learn them.
Okay. So last, anything you want to say to the Chinese developers? At the last.
Yeah, I mean, I hope you found this presentation interesting. I hope that some of you are interested enough to join the community. We have a Chinese speaking portion of the community, but our English speaking portion of the community is very big and has a lot of O1 Labs developers there. So you have good access to O1 Labs developers. I hope you come and check out the incentivized testnet and ask questions and, you know, be involved.
Yeah, sure. Thank you, Nathan. Thank you for presentation today.
Yeah, thanks for having me.
Thank you. Okay.